Okay, so good morning, everyone. Let's get started. So let's recap, right? So if you look back this semester, essentially we learn about three things. So first, we kind of learn about how to interact with the database as a user, right? So essentially, you can create relations or tables like inside database system, and what's going to happen? The database is going to create that for you on your hard drive, right? And then you can start to put data into your database system, or you can start to query your database system. And whenever you have a query, the database is going to bring the data from the hard drive to DRAM and to you as a user, right? And we talk about different query languages that you can use to query a database. On the theoretical side, we talk about relational algebra and relational calculus and different subset of those languages. On the practical side, we talk about SQL. Right? We spent 2 lectures talk about SQL in practice, and we also used another 2 lectures to talk about the SQL, like just to write SQL query together, 2 hands-on sessions. So, and then we talk about essentially modeling, right? So you as a user want to build one applications using a database. Even though you understand how to write SQL queries, you still need to understand, okay, what type of relations do I create in order to build my application? We talk about 2 stages in modeling. The first one is conceptual. The first one is conceptual modeling. We talk about one very specific way for you to do that, and that is entity relationship model. And then we also talk about logical modeling. That is the process that takes as input the conceptual model you have and translate that into a logical data model. And there are so many different choices about logical data model. It all depends on what type of data you have in your database system. So in this course, we will focus on relational model. And the process of logical modeling in this context is to take as input the conceptual model you have and translate that into a relational model. And specifically, we want to translate an entity relationship diagram, which looks like this on the left-hand side, into a relational model, in which all of your data are stored as a whole bunch of relations, and each relation has a schema and also has content. So this is pretty much the second thing that we learned so far. So, and then we talk about essentially about constraints, right? When you are really putting data into your database, you want to make sure whatever you put in there is consistent with all the assumptions you have in your application. And we talk about different ways that you can enforce constraints. We talk about primary key, unique constraint, not null, check foreign keys, right? In the last lecture. So if you look back, like to think about what we have been learning so far in the whole semester, and this is the 3 different components that we have. So in today's lecture, we are going to talk about essentially 3 more things that you can do inside a database. More on the query side, there are more about the advanced functionality that you can do inside the database system as a user. So we will start from recursion, right? How to write like recursive queries inside database. And then we will talk a little bit about null, right? So we talked about that a couple of weeks ago, but there's some leftovers that we can cover today. And then we are going to talk about a fascinating concept called views. Okay, so that's for today. Okay, so let's get started. If you think about all the SQL queries that we are learning so far, right? You know how to write select from where, right? You know how to write aggregation, you know how to write subquery, you know how to write null, right? If you think about all those concepts that we have, how can we construct some applications that we cannot do using the subset of SQL query that we know how to write? So one such example would look like this. You have a parent of relation with 2 attributes. The first attribute is parent, the second attribute is child. Essentially, the data you store in this relation is which person is which person's parent, okay? And then what if I want to ask a query to say, give me all the ancestors of person D? So how would you write such a query? By using all the concepts that we are learning so far. So this query is actually very hard. And let's think about why, right? So to get all the ancestor of person D, you can think about the parent of relation as one way to decode the family tree, right? It's a hierarchy, right, among people, right? Whenever you go one level up, you find the parent, and you go another level up, you find your parent's parent, right? You kind of need to go all the way from the bottom to the top and collect all the information to answer this query, right? So, and we actually know how to go one level up, right? For example, if you write a query look like this, it's going to give you the parent, right, of person D, right? So in this case, you are going to get one person, right, which is C, right, because of this tuple. Right? And then you can actually keep doing this. You can get the parent of C, right, which is the kind of 2 level up. And then you can simply join, right, this parent of relation twice, right? And then you can say, like put these two like variable predicates, then you can get the grandparent of D. Right? In this example, right, C is a parent of D, B is a parent of C, right? So you get person B. But this doesn't answer this query, right? Because we want all the ancestors of D. You kind of need to keep doing this. You need to join the table like 3 times, and then you get essentially the great grandparent of this person D, right? So in this case, if you go one level up, you will find person A. And you can keep doing this, right? If you know beforehand, there's only maybe 10 different levels in the family tree in this database, you can run this query 10 times, then you get your answer. But the problem is, as a user, right? So there, like before you are using before you are doing this, you actually do not know like how many levels that you have inside your database. And as a result, there's actually doesn't exist a single SQL query that works for all possible database instances, right? And the fundamental reason behind it is in SQL, you actually cannot write a loop, right? So if you are using some other programming languages like C++ or Java, right? So you can simply write a for loop, right? So, and then you can actually keep checking whether I have another level in my family tree, right? If I have that, right, then I continue to do it, right? So otherwise, I return all the results. Simply in all the SQL queries that we are learning so far, you do not have that type of functionality. So let's look at another example, right? So here's another example about database containing all the flight information, right? So I have the origin and the destination, meaning that there's one flight from this city to this city. This is the price of the flight ticket. So if you think about what type of information you are storing in this database, you're actually putting together a graph, right? Whenever you have one tuple inside this relation, you essentially have one edge in the graph. For example, there's let's take this tuple as the example, right? You have one tuple containing the information in Munich to Zurich with the price 20. That's corresponding to this edge in the graph, right? You have one edge from Munich to Zurich with price 20. Essentially, this relation is one way to encode all the information you have inside this graph. And what if I want to ask a query saying that, okay, what is the cheapest way to get from PEK to Zurich, okay, from Beijing to Zurich? So in this case, right, we have the same problem, right? We can have all the information about the direct flight, right, by just writing this query. Right? I just query this like the table once. I say, okay, origin is Beijing, like destination is Zurich, right? So and then the price is essentially 100. You get the first tuple, right? But that doesn't answer my query because I want all the ways that you can find in this database to get from PEK to their edge. And then you can actually keep drawing this relation. You can have say, okay, let's join this like flight table twice, right? And then I get all the one-stop flight. Right? So in this case, you are going to get the cheapest flight, if you allow this, is 30, right? Because from this graph, I can from Beijing to Munich to Zurich, right? So I you plug them together, it's like 30, right? So I can keep doing this. So, but again, if you look at all the SQL construction that we have learned so far, you are not able to write a query that works for all the possible database systems, like for all database instances, simply because I don't know how many times I should join the same relation. Right? So that's actually a very fundamental limitation. And today we are going to learn about something to actually accommodate that limitation. And that is by introducing recursive query. So before we introduce the syntax, let's try to understand what we want from a recursive query. If we are building such a functionality, what are things we really want? So let's get really concrete. Let's look at the query that we cannot answer, right? We have the parent of relation. And we want to ask what is ancestor of person D. What type of functionality are we really looking for? So essentially, the functionality we are looking for is to ask the same query again, and again until it converges. So let's look at this. So essentially, in the first time, like we are doing this, we are actually trying to get the parent of D. We can write a query look like this. And then the second time, essentially what we want to do is take as input the result of this, we call ancestor one, and join that with the parent of to get the second level like information. And then I want to ask this query to say, okay, now I take the like ancestor two, the output of the previous step, and join that with a parent relation, and then I get the third level information, right? So, and then in this case, if you look at the second query and the third query, they are actually very, very similar. The only difference is in the second query, I take as input the output of the first query, and in the third query, I take as input the output of second query, right? Other than that, these are exactly the same queries. What I actually want to do is to keep doing this until my result will not change, right? So like in this case, whenever I converge on something, that is my answer, right? So if you look at the query we don't know how to answer yet, this is a functionality that we hope to provide. We want the system to be able to run the same query again, and again, until it converged. So if this is our kind of the functionality that we want, how can we design the syntax to do it, right? So SQL actually gives you a very easy way to express this whole process. And that is by writing something that looks like this. So here, this query contains two components. If you read the first 4 lines, that's one component, and then you have another SQL query in the 5th line. So essentially what happens is that you cannot define a recursive relation R with recursive R, and then you define that as 2 queries. You have one base query union with another recursive query, okay? And then the first 4 lines is going to define a relation R, okay? And then we are going to kind of define semantic later. But after the first 4 lines, right, you are going to define relation R. And then the last line, you are going to write a SQL query involving R using all the SQL constructions that we have learned so far, okay? So essentially what's going to happen is whenever the database see a query like this, it's going to first set R as empty, and then it's going to keep running this base query union recursive query, this part, and set it as new R. And it's going to keep doing this until R does not change anymore. And then it's going to run the last query involving R to get you the answer, okay? And as you can see, this is a very natural way for you to implement a process look like this. Essentially running the same query again, and again. Here, that query is base query union recursive query. You run that again, and again until the result doesn't change, and then you query that result, okay? So this is the process that we want to enable. This is the syntax. So if you have this functionality, right? So one thing you can do to implement this query that getting all the ancestor of person D can look like this, right? So for example, you can have one recursive relation, says that this is relation called ancestor of D. Okay, here's a schema. It has a single attribute called ancestor. And this is the query. You select parent from parent of D. This one will give you kind of one level up of the parent of D. And then you are going to union this with, you kind of join this ancestor of D. In this case, it's going to get essentially the output of the previous stage. Join that with parent of, right? Get essentially like essentially here you are actually doing one level up. So what's going to happen in database is going to first set ancestor of D equals to empty and run this query, and then set that as a new ancestor of D, keep running this query until that doesn't change. And once it converged, it's going to run the last query, which simply give you all the result back. Okay. So now let's look at some examples, because recursion can be pretty tricky. So let's look at this very, very simple example. So you have a recursive relation R with a single attribute R, right? And the query is you select one union, select R from R, and then at last you select star from R. So let's think about the process of database answering this query. So what's going to happen at the beginning is the database will have one relation R, right? Because that's a recursive relation, and that's empty. Okay, you always start from relation that's empty. And then what's going to happen is the database is going to run this query. Select one union, select R from R, given this empty relation. Okay. So and then here what happened? So the thing before union is going to give you one tuple, which is one, right? Because this one simply return one. Union, the second one. The second query is going to return empty because at this stage, R is empty, right? So the second one going to give you empty relation. You union that with one, you get a new relation with only a single tuple, that is one. And then the database is going to take the second R, this one, as input, and run this query again. Right? In this case, what would you have? Again, you have one tuple, which is one, right? And then the second query is also going to return one, right? Because you have a union, right? One union one is also one, right? So you get another relation with the content one. And then the database will say, okay, so if I compare the second relation and the third relation, right? The third step gave me nothing, right? So essentially, like the third relation is exactly the same as the second relation. So I converge. So this is your answer. And then I'm going to take this as R and run the last query. Select star from R, and in this case, we are just like return the whole content of R back to the user. Okay, so this is a semantic about with recursive query. But this can get tricky. So let's look at a couple of more examples. So assuming I have relation look like this, okay, very similar to the previous one, but the first query is still select one and the union. But here I change this a little bit. I select R plus one from R. Essentially, I take whatever is in your previous step, and I kind of like calculate one plus or whatever content you have before, and then use that as the result. What would happen if I give you a query look like this? So again, right, you start from an empty relation R, and then you try to run this query. Okay, so in this case, your like first half is going to return one, right? And then the second half is going to return an empty side because at this moment R is empty, right? So I'm going to have one relation with a single tuple one. And then what happened in the second step? In the second step, I'm going to take as input the second R, right, and run it. The first half of the query is going to give you one tuple, that is one. The second half is going to give you one tuple, which is two, right? Essentially, it's going to take as input the R with a single tuple one, and increase that by one, that give you two, right? Essentially, the third step is going to give a relation with two tuples, one and two. And then you keep doing this, right? So the fourth step is going to give you three tuples, 1, 2, 3. You keep doing this, So, and this gets interesting because this process will never stop, right? So essentially, after doing this, the system will actually throw an error after certain amount of time because it's simply timeout. It simply spend too much time on this. So this is a very common pattern when you are using recursive query and if you're not being careful, right? So not all the recursive query will terminate. And this is simply a very simple example of that. So what happens in a practical database system is simply you are going to get an error out of the database after it try to run this query for a certain amount of time. Okay, so now let's look at another example to make sure we're on the same page about what system is trying to do. So let's look at this. In this query, you are actually having the same query here, select one, union R plus one, R, right? So yeah, so go ahead. I think there's one question. Yeah, go ahead.
I just wanted to ask, namely,
yeah.
for the previous query,
yeah,
couldn't this terminate in reality? Because the thing is, even though this basically goes through all the natural numbers, which are infinite, the thing is, the database in practice is still a machine with only a finite representation of an integer. So wouldn't this at some point wrap back around and then exhaust all possible numbers it can represent and then maybe terminate?
That's a good question. You can try to set the timeout in PostgreSQL as 2 days and see whether it's really stopped. I don't know. To be honest, I don't know. That's a corner case that might be implementation, like implementation dependent. Maybe when you overflow database having protections, it really depends on implementation. But I don't know, right? So that's something you might want to try. Yeah.
Thank you very much.
Yeah. But when we are doing exam, right? So we are assuming we are setting a reasonable timeout, right? Yeah. Okay. Cool. Great. Yeah. So now let's look at this query, right? So this query is a little bit different. So it has the same recursive content. You select one union R plus one from R, but then in the last query, I select star from R, but add a limit 10. Okay. Essentially, I only care about 10 tuples in this relation R. So in this case, what would happen, right? In this case again, right? So the recursive process is going to be doing this, right? It keep like every single time you run the query once, you have one more tuple. But here, what's actually going to happen is very interesting. That is, once you have 10 tuples in relation R, the system is going to take it as an answer because it knows that I only need 10 tuples like from this relation. Okay, so that's another thing the system is able to do. Okay? So essentially, there's some interaction between these two SQL queries. Okay, when the database knows, I only need essentially 10 like examples here. Even if you give me a query that will never stop, right? So whenever you give me essentially 10 examples, 10 tuples, I will take it and use it as my answer. Okay. So how about this one, right? Again, it's very similar to a previous query. The only difference is I will not select star. I will select one aggregation. I will select min R. I take the minimum of this relation. And then I'm hoping that it can give me something. So what would you get here? Will you get a query that actually going to terminate? So in this case, again, right? So you are going to do this recursive process. But the problem here is, if you want to answer the last query, right? So you kind of need to see all the examples like in a relation, like to answer that in the worst case. Like in the most generic case, you need to know all the answers, like in the relation R, right? So in this case, database is actually requires you to have all the tuples of R before it can answer this aggregation query, right? So therefore, in this case, that will actually not terminate. So there's something that's actually very interesting here. So the reason we put the min here is, as you can see, if you are a human, right? If you're looking at this query and you are able to terminate that essentially beforehand, right? That is, every single time I add a new tuple, that tuple cannot be the minimal because I always increase that whole thing by 1, right? So if you have a very smart way to analyze this query, you should be able to see that I actually do not need to wait for all the tuple to ready in R to answer this query, because in your recursive query, all the thing you are doing every single step is to give me a tuple with a larger number that I don't really care about because I'm trying to find the minimum. If you have a very, very smart way to analyze this query, you are able to make this query answering process much more efficient. However, in database, to really deal with a generic case, it will not have this type of automatic analysis of query. I mean, at least not at this level. Okay. So what's going to happen here is very simple. I'm going to kind of mechanically run the internal query again until it converges, and then use that to answer my query. Or I know I only need this many, like 10 tuples to answer this query. I will run the internal part until you have that 10 tuples, and then I take it and run my last query. Okay. So in most of the systems, these are the two things it tries to do. Okay. And of course, there are a lot of research about how to analyze this type of query in a more intelligent way, such that you can deal with more complex queries. For example, like this one, right? So, and this could have been a query that I am able to answer, right? If I'm able to analyze that. But in most of the database systems, yeah, actually in most, if not all the database systems, this is not the case. Okay. So in most of practical database systems, what's going to happen is very simple. You either run the internal query until it converges, or you run the internal query until you reach the number of tuples you need to answer the final query. Okay. Okay. So now let's look at another example, right? To make sure we are on the same page about semantic. So here it's getting a little bit more complex. You have a recursive query, select one, you union, you select R plus one from R, where R is smaller than 5. Okay. And then I try to answer the minimum. Okay. So in this case, right, what happens is going to be very simple, right? You take an input empty relation, you run that once, you get 1, and another one, you get 2, 3, 4, 5, right? So whenever you are reaching this state, if you run that again, right? So you are going to get the same thing, because in the second recursive query, you are only picking the tuple with R smaller than 5. In this case, you are only taking these 4 tuples. You increment by 1, you get 2, 3, 4, 5, right? That's the same as the previous query, right? And then you are going to take this as your answer to answer the final query. In this case, going to give the answer equals to 1, right? Because that's the minimum. Okay, makes sense? Okay, so one more example that could get tricky in practice. So we talk about the difference between union and union all, right? If you still remember, union has a set semantic, okay? So essentially it's going to do duplicate elimination for you, right? If you do 1 union 1, it's going to give you 1. Union all is a bag semantic. If you have 1 union all 1, it's going to give you a bag of 2 examples, both are 1. Okay, so that's the difference. So what if I'm using union all here instead of union? So in this case, right, so again, you start from empty relation. And then after first step, I'm going to get 1 relation with 1 example 1. And then in the second step, I'm going to get essentially the 1 here, and go to take as input 1 and output another 1, right? I'm going to have 1 relation with 2 tuples, and both tuples are 1. Right? You keep doing this, as you can see, the relation keep growing, even though it's the same number, right? But it's going to store that multiple times, and the relation keep getting larger, and larger, right? So, and also this won't terminate, right? So because you never reach a point that you do not introduce any changes to your relation anymore. Okay. So whenever you are writing a recursive query, be careful, right? So sometimes it makes sense to use union, sometimes it makes sense to use union all, right? So it depends on your semantic, but be careful that there's very small difference. I mean, there's very small difference in the syntax, but could have a very large difference in terms of semantic. Okay. Okay. So recursion is very natural in programming, right? So like if you look at C++, if you look at Java, right? So I mean, that's probably like one of the first things that you learn, right? So, and however, as you can see, right, recursion is actually possible in SQL, right? We talk about that semantic, but it's kind of ugly, right? So in the sense that it feels so unnatural in SQL, right? So if you think about how beautiful the thing that we have been learning like so far before today in databases, right? So they are beautiful, right? I mean, like a select from where, it's just beautiful. When you have recursion, yeah, it sometimes looks a little bit weird. It's like something that you add to SQL, right? To like in order to support that functionality. And whenever you are finding a workload containing a lot of these recursive queries, one fundamental thing is the relational database might not be the thing you are looking for. Okay, so the reason you are feeling, I mean, at least I'm feeling that this syntax will be ugly, has a fundamental reason. That is, if you think about all the relational models that we are talking about, right? We always have the mentality model that we are trying to answer some query in mathematical logic, right? So think about how we define our query languages, right? So we have our relational calculus, right? So that's a fundamental thing, like inside the relational database. And because of that, that also gave us a very fundamental limitation of the query language itself if we want to stay inside that logical framework, right? Because as you can see, first order logic cannot really express transitive closure. That is a fundamental limitation of all the query languages that's going to rely on that first order logic semantic. So of course, we can add another layer to SQL, right, to support this type of recursion. But because of this fundamental dependency on first order logic in relational database, sometimes that might feel a little bit ugly. On the other hand, if you have a different data model, right? If you do not store your data as relation, maybe you store that as a graph, right? And as you can see, in those of the database systems relies on graph, recursion is actually a very natural thing to do, okay? So let's just look at one example, right? So the graph database will not be in the exam, right? But I really want you to know two things. One, there are other data models beyond the relational model. And second, for different type of queries, maybe different type of data model makes sense. If you have a lot of recursive query, maybe you should look at the graph database. If you do not, maybe relational database is your friend, right? But there exist multiple possible data models about how you model data, and for each of them, they are good at different things, right? So that is, I want to show that using one example. So one of the use cases of graph database is in semantic web, right? So there's a query language called Sparkle, right? So and that's a query language to get information from RDF graphs. So the fundamental thing is it's not try to answer a logical query anymore. It's actually try to match graph patterns. Okay, so it's pretty much a language for graph matching. So here's actually one database that you could have in your graph database. As you can see, it's very similar to a network database. Okay, so it's not a kind of like a very weird thing like to have, right? So essentially, you have a whole bunch of entities, right? And then you have the relationship between them. You can see this is a graph, and then your query. You can write a query that look like this. You can see it's very similar to SQL, right? But you have some special kind of syntax. So what's going to happen is the system going to take us from this query and compile it to a pattern that looks like this. Okay, so here you can say, I want to find a player club, right? Where so like this player is connected to like striker, right? Like this entity with the edge type position, right? So I have player, striker, position here, right? So that you keep doing this and generate a graph pattern. And then what the system is trying to do, like the answer of the query, the semantic of answering the query is to match this pattern in this large graph and fill in all those question marks using a real entity and return that to you. Okay, so if you have this type of queries, it's getting interesting because you can define like recursion in a very, very natural way. For example, if I want to get a parent of Joe, right, you can write a query look like this. If you can want to get a has parent, right, like kind of the kind of like 2-level up, right? So you can have query look like this. If I want to find all the ancestors, right? So you actually have a special syntax called star saying that, okay, I want to find essentially all the possible paths between member and Joe connected by the has parent relation, right? If you think about what the pattern you are going to have, the first two queries going to have a pattern look like this, right? And the third query is going to actually have a pattern look like this. I can go however many kind of like levels up, like as I want, as long as the type of the edge has parent, and as long as they are connecting two people, right? I want to find this pattern in the graph. And this is a very natural way for you to define recursive query using SPARQL. As you can see, it looks much more beautiful compared with the with recursive construction we have inside SQL. Right? So from this example, right? So like SPARQL will not be in the exam, but I really want you to see that there are kind of different data models. That's very important to know, right? After this course, I do not want you to have the impression that relational model is the best, relational model is the only thing. There are different data models. Each of the data model has their pros and cons. So which one to pick really depends on two things. One is your application, how your data look like, right? So sometimes you can fit your data into both the graph database and the relational database. Sometimes, and even that might feel very weird, right? So, and then the second thing is what type of queries you are trying to ask inside your database, right? So sometimes you have recursive query, maybe relational database is not your best friend, right? It can give you that functionality, but sometimes it might make it very, not tedious, right? Not that strong, but a little bit difficult for you to like write down a query in a compact way, okay? So, but in this course, let's go back to relational database. So let's look at one concrete example here. So assuming we have two relations, this is a relation that we had before. You have the lecture relation contains information about lectures. And then I have a requires relation containing essentially which course is a prerequisite of the other course. And this relation has two attributes, right? So, and the query I want to ask is give me all the prerequisites of the database course, right? So how can you write the query that look like this? So first, this query is not the way to answer this, right? So in this query, I could essentially join kind of requires with requires and lecture, right? I do a sub-selection on lecture to give me essentially the database course, right? And then I join the requires relation twice, right? So in this case, clearly it doesn't give you that, right? Because it's only give you the second level prerequisite of database, right? So if you write a SQL query like this, clearly it will not answer your query. So what can we do, right? So one way to write this is to write a SQL query that look like this. It looks very long, but let's try to read it together. And it's actually not that complicated. Okay, so here as you can see, right? So you always decompose this one into two parts, okay? You always have the definition of the recursive relation, and then the query that you want to answer, okay? So when you read it, you always decompose into two components. In the first component, it defines a relation here called translecture, right? You have two attributes, first and next, okay? This is actually one relation. And then this is your query. This is your base query. And you have union all, and this is your recursive query, okay? Let's call it Q1, let's call it Q2. So in the very beginning, the translecture one is empty. And then when you run Q1, right, what are you going to have? Essentially, it's going to get all the prerequisite relation from requires. Simply, if you look at this, I'm just simply get all the information in the requires relation. Okay, this one give you like the one level prerequisite relation, and that is your initial point. Okay, and then in the second one, it's going to take as input the translecture relation from last step. Okay, well, if you are at the first step, it's going to be empty, right? If you are in the second step, it's going to contain all the information from Q1, right? So you're going to have this and join that with requires. Essentially, if you have like a one level prerequisite relation in requires as input, after Q2 is going to give you the second level thing. Okay, it's going to go one level up, right? So and then essentially you can see this one defines all the prerequisite relationships between two courses, right? If course one is every prerequisite of course B, no matter how many steps you need to take, that thing AB is going to be in this relation after it converges. Okay, and then you read the second part. Okay, so this is how to write this kind of really long query, and then you read the second part. Now the translation relation, the semantics is very clear. It contains a pair of courses that the first course is a prerequisite of the second course, no matter how many levels that you need to go. You join that. Okay, so here is actually an interesting query. So you kind of select like one course from this table, right? And your condition is the next, right, is actually in the result of this subquery. If you look at what this subquery is trying to do, is actually try to get the lecture number of a database with title, the number of a lecture whose title is database, right? So, and as long as the next is in this site, it's going to return the first to you. Okay. So essentially, this is like what happened in this query. Essentially, that's get you all the lecture numbers of like for lectures that are prerequisite of database course. And then if you read this query, it's going to get information from the lecture relation, right, where the lecture number is in this site, right? So clearly, if you put this everything together, it's give you all the prerequisite classes of databases. Okay, so when I'm reading a query look like this, it might look really intimidating, right? Because it's very, very long, right? But like SQL is a language that's very easy to read. You just decompose it. Whenever you see a recursive query, it always has two components. You have the definition of the recursive query, and then you have the final query you want to ask. Okay, so these two are really naturally decomposed, right? Database will always have the result of first part first, and then answer the second part. And then you go like one level down to the subqueries to try to understand it, right? So here we actually have 3 layers of subquery. You try to go level by level, right? So and then you should be understand it. Okay. So whenever we are doing exam, right, when you see a very long SQL query, just don't worry, right? So it's very easy to read, right? I mean, especially the query in our exam and in our course. If you go to real world, there are SQL queries with maybe 100 lines long, right? But that's a different story. Okay. But all the query that we have, probably this is maybe the upper bound of how many lines we have. Okay, great. So that's all about recursion, right? So and like again, this is something that if you really want to learn about it, just open a real world database system and play with it. And that's probably the most easiest way for you to understand recursion. Yeah, so that's all for recursion. Let's take a break. When we get back, we are going to talk about views. Okay, so I'll be here to answer whatever question you have. Yeah.
Professor.
Yeah, go ahead. Yeah, go ahead.
There seems to be an issue with slides on the website. So currently, part 2 links to the slide for part 1, and part 1 we can, and part 2 we cannot access.
Oh, sorry. Yeah, let me. Okay. So let me try to fix that right now. Yeah.
Yeah, that would be great if you could have them for the second part.
Sure. Yeah.
Thanks.
Okay. Yeah. Okay. So, other questions? Yeah, go ahead.
I'm a bit confused about the union all in this example, because we said that union all, or at least in the last example with union all, this caused a problem. Why does it not cause a problem here?
Yeah, so I think in this one, so I think so we look at this, right? So if you do not have duplicates, that will not cause a problem, right? So here, even you have union so even you have union all, I think in this case, okay, so let me think about it actually.
But with union all, there will always be a result of this second query, so it should always grow, right?
Yeah, so give me a minute. Yeah, so I'm trying to think about it. No. Okay, cool. Okay. So when will union all be a problem? Okay. So let's think about this as a graph. So I think that actually makes things easier. So assuming you have a graph, yeah, this is a very ugly color, sorry. So assuming you have a graph, right? So like you can think about this kind of lecture table as a graph, right? So like you have all those prerequisite relations, right? Like something like this. So when will union all become a problem? Union all become a problem when you have a loop in the graph, right? So because once this thing is in the graph, so once this node is in the result, running it again is going to get itself. So it never stop. However, when you have a graph without a self loop, I think that should be fun. And here's the reason. So assuming at the current stage, I have all of this node here, like in my result. Okay. So I start from empty and I have all of this. And then if I run this again, I'm going to get, I see. Okay, so like here, if you use union, there's no problem at all. But let me think about union all case. Yeah, and give you a precise answer after the course. Is that okay?
Yes, thank you very much.
Yeah. So like this something I need to think about like a little bit more carefully before I give you an answer. Yeah, sorry. Yeah, but if you do union, there's no problem. Yeah, right. But I believe union all is fine, but I need to write down the precise condition. Okay, so let's continue. So in the first half of the lecture, we talked about recursion, right? So in the second half, let's switch gear and talk about some other functionalities inside database. So let's first talk a little bit about null, right? So we talked about that before, but there's actually some additional content. And then we are going to talk about views. So let's start from null. So let's try to refresh our memory about this. So essentially, null is a state, not a value. When you have a null state inside your database, right? So essentially try to kind of whatever arithmetic operation you are doing with null, we will have its own rule, right? So if you have null plus 1, that's going to evaluate to null, because like if you do null plus 1, that's still do null. Null times 0 in database is evaluate to null, right? So, and when I try to compare different null state, it's going to give you one value in a 3-value logic system. It's not only true and false anymore, but you have another value called unknown. If you compare two null value, null is null, going to give you unknown. If you compare null, for example, with a number, right, it's going to give you unknown. If you compare between null, again, it's going to give you unknown. Whenever you have those predicates involving unknown, you are going to follow a very natural, essentially a 3-value logic system. Okay. So just as one example, we will have the lecture table, right? If you write a SQL query, it look like this, right? So in this case, it will only give you 2 examples. It will actually get rid of the first example, because if you evaluate the first half, it is unknown. If you evaluate the second half, it's still unknown. If you do the OR, it's still unknown, right? And here, you are going to get something look like this. So you can, when writing a query over null, right? So that actually introduce a whole bunch of corner cases, right? So this is just one corner case. I mean, if you do not have null, this query might look like a trivial one, but when you have null, it's going to actually get rid of examples, right? So, and again, null is a state, not a value, right? So you cannot compare null, but you can check whether a state is null or not, right? So if you say null, it's going to give you true instead of unknown, right? So again, in this case, right? So if you compare these two queries, right, they are going to give you a different result. In the first query, you are comparing whether person, like whether personal number equals null, right? Of course, it's almost always going to give you unknown, right? So you are going to return nothing. When you have person number like is null, right? It's going to give you the first tuple. Right? So that's what we have before. So what's gets even more tricky is you have null in aggregations, right? So, and that's something we are going to talk about today. So what if you have a relation with null states, and then you have a query involving aggregation? So when you have this, there are 2 different cases. The first one is null is involving is in the group, right? Another is null is in the value, right? So let's go to the first case. So whenever you have null in the group by attributes, so essentially all the nulls going to form a single group. So for example, here I have relation employee with employee ID, the name, the department, the salary, right? And then I have the group by query. I group by department. Essentially for every single value of department, I have a group, and then I aggregate them. So if you have this, all of the null values, here I have 2 null value in department. I have 3 value of IT, 1 value of finances. So here you are going to have a result with 3 tuples, the IT, the finances, which is actually like the easy one, and all the null value is going to become one group, okay? And what if you have null in the value, right? So after I do the grouping, within that group, I have null. What would happen? Most of the operators will ignore the null value. So for example, if I have a query look like this, for each group, I want to calculate the max the maximum salary. Okay, so in this case, if you look at, for example, the IT group, right? I have IT 2000, IT 1000, IT no. In this case, most of the aggregation operator, when you aggregate 2000, 1000 no, it's going to just ignore the no. It's going to give you 2000, like in this case. Okay, so similarly, if you look at the null group, you have two tuples, 2500, and you have null. In this case, if you do the max, it's going to give you 2500 instead of giving you a null, right? So when you do aggregation, when there's null in the value, most of the operator will ignore the null value. And we say most simply because there are other cases, right? So we are going to go through them. So whenever you have count star, okay, so this will not ignore the null. So here, essentially, I'm trying to count how many examples are there in the group. Okay, so in this case, it will actually not ignore it. Okay, so let's go to this example. So here, I group by department again, right? So and for each group, I count star. Essentially, I will say, okay, I want to count how many tuples are there. So, and in this case, you have IT, right? So you have 3 tuples, right? So and one's here, another here, and 1 tuple, 2 tuples, 3 tuples, right? Even though there's no value, right? You are actually not going to like ignore it. Okay. So here you are going to have 3 in IT, 1 in finance, and 2 in null. Okay. But if you make that really concrete, if you put the attribute number here, like if you put the attribute name here, it will actually ignore the null. Okay. So here, if you have department, group by department, and for each group, you want to count salary. Okay. So in this case, you are talking about this attribute, and the database will actually ignore the null value. For example, here you have IT, you have 3 examples in IT, I have 1 salary is null. Whenever you count it, I'm going to ignore this. Okay, but when you write count star, it will not ignore it. Okay. So now let's look at another example. So sometimes we have null values when they are like after the operator ignore all the nulls, when they if it's working with an empty site, it will actually return null for you. Okay. So now let's look at this example, right? So here in the same query, like I want to group by department, and for each group, I want to calculate the max salary. In this case, we look at this table. All the group will have all the salary equal to null. Yes, and this max operator is going to ignore all the nulls, but after it's ignore all the nulls, it's going to leave with an empty site, right? And there's nothing else there, right? Because I already ignored everything. In this case, if you run this query, you are going to get null as the answer for each group. Okay, so this is another corner case that's important. Okay, so another interesting thing involving null is there are actually operators that can introduce null. Okay, and one of those collection of operators is something that we call outer join. Okay, so that's a different type of join. So there's left outer join and there's a right outer join. So let's just go through them one by one. So when you have a left outer join between 2 relations on certain column, for example, here I have one relation ABC and another relation CDE, they share C, right? Whenever I'm doing my left outer join, what I'm going to do is I'm going to keep all the tuples from the left-hand side, right? So in this case, I have 2 tuples in my left-hand side. I'm going to keep them right here. And then I'm going to try to join it with the second with the relation on the right-hand side. If I'm able to find a matching tuple, for example, for the first tuple for C1, right? So that also appears in the second, like in the right-hand side, I'm going to do join as normal, right? But if I cannot find a match, for example, for C2, right? I cannot find a match here. I'm going to put null in the unmatched position. Okay, so if you do a left outer join between these two relations on attribute C, this is what you are going to get, right? So this is just one operator that could introduce. So this is just one operator that could introduce null. And on the other hand, there's a right outer join, which is very similar. Essentially, you keep all the tuples from the right-hand side. So here, both tuple involving C1 and C3 will be here. And then you try to do the join with the relation on the left-hand side. If you can find the matching tuple, you put it here. Otherwise, you just fill the value with null. Okay. And then there is the full outer join, which pretty much keeps the tuple from both sides. And then you fill the other unmatched position with null. Okay. So in this case, I will have two tuples, right? Like matching left-hand side, have another one matching the right-hand side, right? Whenever I cannot find the matching tuple, I just fill null with it. And inside database, right? So you can actually write outer join. So here the syntax, you can select whole column from one relation, left outer join, another relation, and you can do whatever you want here, right? So yeah, so similarly, you can do full outer join, right? So as the name implies, that's when we're going to give you the full outer join. Cool. Yeah, so that's a little bit, I mean, that's like kind of some content that we left over like from a couple of weeks ago, right, involving null. So the tricky part is more about aggregation and also about outer join, okay? Okay, so now let's move on. Let's talk about another concept inside database that you might find useful in practice, and that is called view. It's actually very interesting. So before we talk about that, so let's look at, oh yeah, sorry, there's actually one corner case we want to talk about before we talk about views. Sorry. So, and that is when we talk about data manipulation language, we talk about the user can actually add, delete, or modify data in a database, right? You can insert data, you can update, you can delete data, right? So, and we talk about different syntax, right? So, for example, you can insert it, you can delete, you can update. So there's one tricky case that I really want to go through before we talk about view. So that is, for example, I have a relation look like this. I have the prerequisite and I have the follow-up. So, and my query is, I want to delete from requires, where the prerequisite is in select follow-up from requires, assuming this is my query. So this query gets tricky because, as you can see, I'm deleting from this relation, but I'm also using this relation here, right? Like inside my condition. When you run this query, what is the semantic, right? So what is the database trying to achieve for you? So in this case, what database is trying to achieve is to decompose this into two different phases, okay? So first one is going to mark all the tuples which are affected by the update, okay? It's going to actually run this SQL query and try to mark up all the tuples that you are going to change without actually changing them, okay? That's phase one. And in phase two, it's going to implement all those changes. In this query, it's going to update all the values, essentially all deleting all the 4 tuples. This is very important because if you do not do this, there could be a problem, okay? So now let's look at like what if the database doesn't have this kind of two-phase structure. So what if I kind of have one tuple, whenever I find a tuple, satisfy the condition, I remove it, and then I find another tuple, satisfy the condition, I remove it, right? So in this case, for example, here, you have a relation A, B, B, C, C, D, right? So it's like a chain, right? So clearly BC satisfies this condition, right? If I remove that immediately, I will not find another tuple that satisfies the position. Then I'm going to give you a relation with 2 tuples. However, if I do the markup, I'm going to find 2 tuples that need to be deleted. If I delete both, I'm going to give you essentially like a single tuple, right? So as you can see, if the database do not follow this two-phase structure, you could have a non-deterministic result, right? So what if you delete this tuple first, or delete the third tuple first? You are going to have different result, right? So by having this kind of two-phase kind of like structure, right? So database is going to give you a kind of deterministic result, even if you are using the same relation you are updating. Okay. So in database, the first one is not something you're expecting. The second one is what you are expecting. Okay. So it's a kind of a corner case. It's actually not a corner case. It's simply the semantic of updates. Okay. Okay. So now let's talk about views. So we talk about relation, right? So which is actually like give you a very nice way to achieve data independence, right? So whenever you are writing a SQL query, you as a user actually do not care that much about how the data are actually stored, right? So it gives you a way to talk about your data without knowing kind of the for example, different orders of data, something like that. So we can actually go one level up in achieving data independence, right? So, and that is by through something that we call view. So that's at an even higher level of abstraction. And the thing that we try to provide for the user is something called logical data independence. So the goal is the user can use view without worrying about how relations are organized underneath the cover. Okay, that's one layer up, over the relation layer. So in a database, a view is simply the result set of a stored query on data, which a database user can query just as like they would essentially user can just use a view as if it is relation, right? And the view is defined as a stored query on data. So this is going to get very concrete very soon. Okay, so how to define a view? To define a view is similar to how to define a table or relation inside database. So here's a syntax. You create a view and you put the name of the view here as a SQL query. Okay. So what system is going to do is to give this SQL query a name, which is this, and then you can use the view as if it is a table. So there are actually very fundamental difference between view and relation. Well, we are going to see that later. So let's go to one example. This is our flight table, okay? From original place to destination, and here's a price. So what you can do is let's find assuming you want to say, okay, so I'm really curious about all the flight from Beijing to other cities, right? And what you can do is you can actually create a view called flight from PK, right? And here's a query, select star from flight where original equal to PK, right? Something like this. And then after you define this, you can actually use this view as if it is the table. Okay, you can query this. You can select from this view where destination equals to Zurich, right? And this one will give you this tuple. And then logically, this view, given this input, is going to look like this. Okay, but the difference is this table on the right-hand side is never materialized. Okay, so whenever the user are using this view, the system is going to run that query for the user. Okay, whenever you create a view, this relation is never materialized. Okay, so what's the difference between view and table, right? So that's actually pretty natural. So let's put them side by side. Okay, so let's say we have one case, we create a table, flight from PK, right? Select star where original equals to PK, and we have another create a view here, right? And then we insert one tuple into my original relation, for example, PK 200, and then I select from this table, right? Flight from PK where destination equals Zurich. In this case, on the left-hand side, if I'm using a table, how many tuples am I expecting in my result? In this case, I'm expecting one tuple. Why? Because whenever you are inserting this new tuple into the flight table, you will not change the result of other tables, right? So if you are like putting flight from PK as a table, this insert query actually will not impact the result of the flight from PK table. And then whenever you are querying the flight from PK table, you get the original result, right? So essentially you have one tuple in the result. However, if you are doing the view, whenever you are inserting another tuple in flight and you query the view again, whenever you are querying it, what's going to happen is the database going to actually evaluate the view on the fly using the latest data, right? So here you are going to get two tuples in the result, right? By putting this side by side, you can see the difference between table and view, right? Table is kind of giving a name to a query that you can keep using it. Table is you have a query, you run it, and you save it, and then you can reuse the answer of the query again and again. Maybe your data start to change. Maybe if you run a query again, the table would be different. But because the table is already materialized, changing other relation will not have impact on the table. But it will have impact on the view because the view is simply giving a name to a query. Okay, so that's the difference between table and view. So here's actually what we mean by view is logical. It's actually not being materialized. Right? It's a different name for query. So why do we want to use views, right? So there are multiple reasons behind it, and you are going to see them in practice. So let's just use some very simple example to illustrate them. One way that people are using view is to use it as some way to do access control and preserving privacy, right? So just like one example. So you have the flight table, right? So assuming you have someone in your organization who only supposed to see all the flight from PEK, but not from other cities, right? So in that case, you cannot give that person the full access on the flight table, right? Because in that table, there are flights that you do not want that person to see, right? What can you do? Here, what you can do is you can actually define a view contains information that person can see and only give that person the access to this view, right? So in this case, you can give that person so essentially like access to this view, and then that person can only see all the flight originated from a certain city. If there's some reason that some flight are secret to that person, right? That user will never have access to that because that user only have access to the view, but not the underlying table, right? So this is just one simple example about how to preserve privacy using views. So here's another example, right? Assuming you have a test table, right? So you have your personnel number, lecture ID, and the grade, right? So as you can see, the grade is a very sensitive information, right? You do not want everyone in the university knows your grade, right? So that's your information, right? Why do other people knows about that? And then in this case, right? So maybe the information of personnel number and the lecture ID is still useful for some people, but not the grade. So you can create a view with a like containing one projection that only contain information about personal number and lecture ID, right? Without the grade, and you can expose this like test view to a user, and then that user will never know your grade because that user doesn't have access to the test table, but that user can still use the information to do something useful, right? So this is a kind of another example. Is make access control inside database sometimes much easier. And another thing is about usability, right? So this is also very natural. When you have views, your query become shorter, right? So for example, I have the flight table and I create a view containing all the flights from PEK, right? So, and the user can actually use this view to write query easier. For example, if you want to find all the flights from PEK to Zurich, if you do not have this view, you can need to write two conditions here, right? You need to specify the original city and destination. If you have this view, right? You only need to specify one condition because the other condition is kind of inherent in this view. So in this example, that's going to save you one predicate, right? So it's already make your life a little bit easier. But the saving here might not sound too big, but in practice, when you have a real-world database system with thousands of tables, by using Vue, sometimes you can make the process of writing queries much easier. Okay. And third way of using Vue is actually try to use that to encode like the kind of generalization. Okay. So assuming that you have an employee table, contain employee, you have data about professor, data about the assistant, right? So in this case, I have all the employee here, I have ID, I have the name. Some of them are professor, I put ID here, I have the room. Some of them are assistant, I put ID here and put the course as the TA. So what if I want to like have a global view of my organization, right? So in this case, once you can do is like, for example, here, the professor doesn't have a name, right? So, but however, like you can imagine whenever you are building applications, like often, like you want, for example, whenever I have a professor, I also have a name. So in this case, you can have these three as a base table. And then you can create a view for professor by drawing employee and professor data on ID, and then you return everything, and then you can keep using this professor table as if it is you can use the professor view as if it is a table. Whenever you are querying this professor view, you have the professor ID with the name with the room, okay, all together. And similarly, you can create a view for assistant, right? So under the cover, your base relation is very beautiful. There's no redundant information at all, right? Your employee, ID, name, professor, ID, room, right? But if you only expose these three relations to a user, that's very difficult to use because every single time I want to find the name of professor, I need to join these two relations, right? So, but if you create a view, I can only use, so I can just use the professor view. Whenever I'm using that, logically, I get something very beautiful, right? I don't care how your physical table are organized. I don't care whether your physical table has the professor room and professor name in the same relation. I don't care. All I care about is logically, that is the functionality you provide, okay? So that is why we say relation give you physical data independence and view give you logical data independence. And of course, there are different ways that you can do generalization, right? For example, you could do this way. The base table could be a professor. You have ID, you have name, you have view. Your ID, you have name, you have room. For this time, you have ID, you have name, you have TA course. And for other employees, I only store ID and name, right? So, and this three relation essentially store a disjoint partition of all the employees. But what if I want to query all the employees, right? So here you can actually create a view for all the employee by just doing the union between these three different relations, right? So you can have the ID and name from professor, ID name from assistant, ID name from other employees. You union them together. And in this case, whenever I'm trying to query all the employees, I can simply using this view without without doing the union, like in every single query I'm going to write. Right? So this is just another way that the view can make your life easier, right? Give you this type of data, like logical data independence. By using this view, you actually don't care how the data, how the relations are kind of organized under the cover. It might be a single relation as this. It might be three different relations. That's not the job of the user to worry about that. So another thing is, once you define a view, how are they being evaluated? So because view is simply a name for a certain query, whenever you are evaluating a view, so the system is going to do a query rewriting. So for example, still this example, I have a view flight from PEK, right? And I'm querying this view. So what's going to happen when you give the query to the system is that the system is going to rewrite this query, going to replace the name of this view with a query that defining this view. Okay, so in this case, you're going to like replace flight from PK with this query, and then try to run this query for you. And then it can do some query writing to make that much simpler, right? And then this is the job of database management system to automatically deal with that for you as a user. Okay, so there's really no magic. You think about view as the name you are giving to a query. You are using it. Whenever you're using it, whenever system try to answer the like query involving a view, it's going to replace the name of the view with the defining query, and then just answer that query. Okay, so that's what happened during execution. So things get a little bit more interesting when you think about, can we update a view? Okay, and we told you that you can use view as if it's a table, but you can update the table. Can you update a view? So this question is interesting because we need to first understand what do we even mean by that, right? View is a name for relation, and what do you mean by updating it? So here's one way to define that. So let's say there be a whole bunch of base relations, their relations, R1 to Rn, and you have a view defined over them. And this view is defined by a query Q, take as input R1 to Rn, and give you an output relation. If the user want to update this view, for example, update this view from V into V prime, essentially what we are trying to do is to try to find a set of updates to the base relation and turn them into R1 prime to Rn prime, such that if you evaluate the query Q over R1 prime to Rn prime, you get V prime. So this is just what it is. You have R1 to Rn, your query give you this view, give you this result of the view, right? And then if you want to update that from V to V prime, under the cover, what you are really trying to do is to find a whole bunch of updates on the base relation, such that evaluating the same query going to give a view with the content that you want. Okay? So by saying updating view, this is concretely what we are talking about. So for example, I have the flight table. I still have our view flight from PK, right? And then assuming we want to delete from that, for example, we want to delete all the flight with price larger than 500, what's going to happen is I want to update my base relation such that running this query is going to give you a view with the only 2 tuples. And in this case, I'm lucky because I'm able to find that. If I remove the PK to the SFO, like kind of tuple, this will give you the content that you want, which is removing the PK and SFO tuple in like in this view. In this case, if you are deleting from this view using this query, you are actually deleting this tuple in the base relation. So as you can see, right? So there's one fundamental question we need to understand. That is this always possible, right? Can we always find the updates on the base relation such that it reflects the update you want to do on the view? And second, are all those changes always unique? Do I always have a unique way to update my base relation such that you get the update on your view, right? So these are really 2 fundamental questions that you need to understand when you are trying to update the view. I mean, when you are trying to build a system that support updating of the view. So the answer to these 2 questions, not surprisingly, right, are both no. Right? It's not always the case that you can always find an update of base relation to reflect the update of the view. And even those updates exist, they may not be unique. And that is why there are views that are not updatable. You cannot update every single view in your system. For example, projections are hard because whenever the view are losing information, your updates might not be unique. And we are going to see one example. So let's take this example, right? So it's an apply table. You have student ID, you have student name, you have the major of the student, you have the decision of application, whatever. And then I have a view, which is a projection. Okay, I just do some filter on the apply table. I take the major equal CS, decision equal to Y, and I only project the student ID. In this case, if you want to insert it, you want to insert into this view a new student with student equal to 2. It's not really easy to update because you don't know what to fill in for all the other columns, right? So this is just one case that when you are doing projection, there are so many different ways you can update your base relation to to reflect the update you want on the view. There are so many different ways that are not unique. You actually don't know which is the right thing to do. And that's actually give you one case that this view is not really updatable. And aggregation could cause a problem. So here's actually another example. You have a very simple relation with a single column R, contains maybe 9 different numbers, 1 to 9. And then you have a view, calculate the sum. Okay, I want to calculate the sum of this relation, right? So, and then whenever I want to update this view, I want to increase the value in the view by 1. In this case, right? So there are actually so many different ways you can update your base relation. You can turn your 1 to 2, you're going to be fine. You can turn your 2 to 3, 3 to 4, and you can turn 1 to 0.5, 2 to 2. You can turn 1 to 1.5, 2 to 2.5. You are going to be fine, right? So there are so many different ways you can update your base relation to reflect the change you want on the view, and that's cause problem. And this is actually another example of a view that's not updatable. So on the other hand, some of the views are easier to update, right? So assuming we have this relation, right? So the primary key is R, right? So you have another attribute C, and you have a view which is just the original table. And whatever you update, you want to say, okay, I delete one tuple from the view. Right? You can simply find the corresponding tuple and delete it, right? So there's a unique way you can update your base relation to reflect the update you want on the view, right? So this is just one example of a view that kind of easier to be updated. So in real world system, right? So here's what's going to happen. So the principle behind SQL is try to make sure whatever it's doing is deterministic. At least it's try to do that. Whenever there's uncertainty, it often refuses to do it. Okay, it's very, very conservative with respect to view updates. So in many practical systems, at least in the standard, a SQL view is updatable if and only if, first one, this view only involves one base relation. Whenever the view involves a join, right? So it's actually not updatable in SQL. Right? It might be updatable in theory, but in practical system, it's not updatable. The view need to involve the key of that base relation. And the view does not involve aggregates, group by, duplicate elimination, so on and so forth. Whenever a view satisfies this condition, it's updatable. You can update it. So the intuition behind this rule is really try to maintain a one-to-one mapping between the view and the base relation. And this doesn't give you all the views that could potentially be updatable. Right? If you think all the views, they are kind of a large set of views that's updatable in theory, but SQL essentially only allows you to do a very small part of it. Okay, so updating view could be very tricky in practice. Whenever you are building one application and need to update the view, go to the reference of the database system that you are using and try to learn about that. It might be PostgreSQL, it might not be PostgreSQL. People often have different kind of different assumptions on what type of view is updatable. Okay, cool. So I think that's all for today. I'll be here to answer your questions. Otherwise, I'll see you in the next lecture. Yeah. Thank you.
I have a question.
Yeah, go ahead. Go ahead.
In the first lecture, you showed the example with the airplanes and the stops.
The first part, right? So here,
Right in the beginning.
so here, right? You mean this
Yes. Then I have a question.
Sure.
How could we solve the problem that when 2 and 3 hops would cost the same, but 4 hops would be cheaper if the query would end after it gets the same result as before?
Okay, so let's try to, okay, so, okay, let's think about that. Okay, so let's think about this. I understand your question. Your question is assuming I have, oh, no. Okay, so here's your question. So assuming I have a 3-hop flight with certain price, right? And then I also have a 4-hop flight with a different price, right? And then the system will not converge until it finds the 4-hop flight, right?
No, actually, the question is, so imagine we have a 2-hop flight, which costs the same as a 3-hop flight. Yeah. And then we said that the recursion would repeat until R does not change. So, but now imagine a 4-hop flight would be cheaper than the 3-hop and the 2-hop price.
Yeah.
So how would we know where to end? Because normally, as I understood it, we would end right after the 3rd hop because it would return the same price as the 2nd hop.
Oh, no. So essentially, like when you're doing recursion, right? So like your recursive relation will be CT1, CT2, and price.
Yes.
Right. So you are going to look at this combination. Right. For example, after the 3-hop, I find a 3-hop flight from CTA to CTB with price whatever like a C, right? So like even if the 2-hop and 3-hop have the same price. Okay, I see. So essentially your question is that okay, so I see your question. But here, if you are doing union all, it should be fun, right?
Okay, because union all looks at all combinations anyway and picks the minimum. Is that right?
No, so like your union all going to have the back semantic, right? Like if you like introduce one additional. Okay, I actually see your question now. Okay, so if I were you, when design this, so because we didn't show this query here, right? So okay, no. So yeah, so like now my comment about union all. So if I were you, I will put a hop here.
Okay.
That will fix your problem, right?
Yes, I think so.
So I have 2 hop, then I have 3 hop, right? So these 2 are different, right? So like whenever I mean this is a very good question. Whenever you have concern like this, right? So whenever the query will stop earlier, one way is you kind of extend the state.
Okay,
right?
so it picks both the minimums of the minimum hop and the minimum price. Okay.
Exactly. You start to redefine what you mean by converge.
Okay, that makes sense.
That makes sense, right?
Okay, thanks a lot.
Cool. Yeah, sure.
Have a nice day. Bye.
You too. Bye. Yeah, no. So like in this case, right? So the recursion couldn't, right? Because for example, after you have the 4, right? So and then if you cannot find the 5, then you converge, right?
I have two questions.
Sure.
First of all, we have a forum on Moodle where we can post questions. And I would like to know if it's just among students, like just a forum for students to post questions and the other students supposed to answer the questions? Or is it meant to be answered by the teaching assistants?
I think it's supposed to be answered by the teaching assistant. Yeah. So if there's a long delay, I will let them know to make sure we answer your question in a shorter amount of time, right? So like your concerns, there are questions there not being answered after a while.
Yeah, I saw some questions were left unanswered for like 5 to 7 days, and one question is really interesting to me because it's about the reading assignment. So up to what I saw at this moment, we have so much to read in the textbook. It's like 1,000 pages, I'm not mistaken. And when we go to the official website, sometimes we see the lecture reading assignment. It's the whole chapter, like chapter 4, chapter 6, chapter 8, and there really much information to read. I would like to know if the exam cover the whole book, or how can I say? Do we need all? Yeah.
Yeah. So I mean that's a very valid concern, right? So one thing that we are going to do is we have 2 lectures we will use as exam review that we are going to define the scope.
Mm-hmm.
So it will be usually it's the last lecture before Easter, but this semester Easter, yeah. So it's going to be maybe the 3rd or 4th lecture after Easter. That's our first exam review. That we are go through all the results, and we are going to look at the previous exam, and we are going to go through the kind of the assumption we are making, and also the scope, what we are expecting you guys to know, right? So and we are going to have another exam review at the end of the end of the course, right? So hopefully these 2 can help you to choose which essentially which section to read.
Yeah.
So will that fix your concern?
So it means for this moment, at the moment you're expecting us to read the whole chapter as stated on the official website, right?
If up to me, it's not whether I'm expecting, right? So I hope you read the whole chapter. Yeah.
Yeah. Okay.
Yeah. So I really hope like you can read the whole chapter. But we are going to have 2 exam review sessions that we kind of define very precise scope, which is going to be smaller than the whole chapter. Yeah.
Yeah, I get it. And about the exercise 3 on Moodle, I have to say that the last 3 exercises were somewhat overkill for me. Is that something like we have as cases to study, or is it something we're supposed to be able to solve after this course?
So like you mean the last 3? So yeah, sorry. Like you mean the exercise, or you mean the lecture?
The exercise 3 on Moodle. So the last 3 questions where we have to write SQL was really complicated.
Yeah. So let me see it. So
it's about recursion. If I'm not mistaken, recursion is somewhat we have just covered today, but the exercise 3 was from last week and stuff. And maybe because of that, it was so complicated for me. But it's just for information, for your information.
Yeah. So like, can you give me one concrete example? You mean SQL 3, exercise 4, right?
So the last 3 questions of the exercise 3, where we have to use recursion to go to the deeper level and stuff. But
okay.
Well,
okay, let me the last 3 questions. Let me look at it.
Yeah, I think after this.
Oh yeah, sorry. I think this like some problem on our side. I think there's a mismatch between exercise and the lecture. Sorry about that. Yeah. So, but I think after today, you know how to answer those, right?
Yep.
Oh yeah. Sorry. So I mean the problem on our side. Yeah. So sorry about that. Yeah. So I think it will get better like down the road. Yeah. So I think there's some mismatch. Yeah.
Okay. That's what just for your information. Okay. Thank you very much, and have a nice
Thank you.
afternoon. Bye.
You too. Bye.